Javier García de Abajo received his PhD in 1993 from the University of the Basque Country, where he worked on the interaction between kinetic ions and surfaces under the supervision of Pedro Miguel Echenique. He then spent 3 years in Berkeley National Lab and returned to Spain to become staff scientist at CSIC. Later, in 2008, he was promoted to research professor. Nowadays, he's an ICREA research professor and leader of the nanophotonics theory group at ICFO. His research there focuses on using nanophotonics to unlock potential applications in microscopy, sensing, or information processing. Javier García de Abajo is a fellow of the American Physical Society, the Optical Society of America, and the Electromagnetic Academy. Hello, hi, Javier García de Abajo. It's a pleasure to have you here, and thank you for agreeing to the interview.
Thank you for the invitation to come here to your institute.
First question that we had if you ever considered doing something other than physics?
Of course. I mean, like many of us, I guess, no, we have a natural tendency to like doing things, learning how things work, from the natural world to bio things to small mechanisms. And then I think that has interested me all along this time. And so physics is just part of it. Once you become more and more experienced in it, no, then you learn how to love it more and more. But of course, I think at some point I was also hesitating whether I should do maybe philosophy or pure mathematics or even biology. I think it's the best attitude, I think, is to just try to learn about everything. There are so many exciting things in every discipline.
I guess we can summarize it as physics can also be an acquired taste, or any discipline for that matter.
Also, I would say that physics is very multidisciplinary in a way. It's very easy to combine with other things. And so there are many disciplines that have emerged from physics, even derived disciplines like, I don't know, econophysics or biophysics. Or physics allows you to understand the world in a certain way, and it's very cross-disciplinary. But besides that, I think even taking an approach to learn other disciplines very much in detail, for example, I don't know, some experimental zoology, I think that would be, I could be passionate about that, I'm sure, no? Just entering there and learning about the complexities and the secrets of the animal world, right?
For students who are now pursuing or starting a scientific career, PhD students or undergraduate students, they, I think, often don't know how a career in science actually looks like. So maybe you can describe which steps you took in your career.
So I was studying my bachelor in the University of the Basque Country in Bilbao, and then I moved to, after a quick experience, starting a PhD in London on superstring theory, which I decided it was not for me, too abstract, also the atmosphere in the group, etc. No? Then I moved to San Sebastian to do a PhD in atomic collisions in solids, solid state physics, somehow cross-disciplinary in a certain way. Then I moved for a postdoc to Berkeley to work on surface science and synchrotron radiation, photoemission, etc. No? And from there I moved back to Spain, where I obtained a position at the Spanish Research Council, the CSIC, and there I was starting to work on the nanophotonics as a natural extension of working with previously with atomic beams, with electrons, etc. No? From the theory perspective, it's very easy to move to other types of waves, no? So electromagnetic waves, and so nanophotonics was booming at the time in the early 2000s. And from there, it's just a continuation. And then I started working on graphene, 2D materials, as a sub-branch of nanophotonics. Then I moved to ICFO after a sabbatical in Southampton, extended sabbatical. All along this way, I've been also working on electron beams and free electrons. And now there are exciting prospects for free electrons, right? So in the end, it was like a continuation of studying something. No? You were studying physics, then you continued studying physics during your PhD, postdoc, etc. So it's just a continuation. That's my perception, right? Now, is this a good advice for somebody who's starting now? Maybe not, because things have changed now. So everybody is more aware that you have to have the qualifications to find a good employment somewhere. And so you have to have certain ticks, like publishing good papers, eventually get good grants, visit the relevant institutions, etc. No?
And along those lines, science as a career can be a very rewarding one. What are your, in your opinion, the most rewarding aspects?
I guess is the feeling of freedom, that basically you are free to work on things driven by self-interest and motivation. I think it's enjoyable. Then, I mean, waking up every morning and just having this feeling, oh, I still have to do these things that I like, right? I think that's very rewarding. Of course, it doesn't happen all the time like this, no? And also, this feeling of being a community worldwide, when you go to conferences and eventually you become friends, long-term friends with many of the colleagues that you see here and there in the world, and it's like a small family, right?
Where the least rewarding aspects, the most challenging parts of being a scientist in day-to-day life?
Well, a clear one is if you decide to become a scientist, and then eventually you have to get a position. So sometimes that comes naturally, like as a result of maybe you are super successful, but in general it's always a hard process, no? And it's very competitive at the moment. But essentially combining your personal life and your professional life, if you are really deeply into working hard in physics, no? As a scientist, involves changing the locations, no? You live in different places, and eventually you don't even know where you are going to settle down in the end, no? That can be tough. Apart from that, funding is extremely competitive.
But for now, I want to switch gears a little bit and discuss more scientific aspects. What is nanophotonics?
Nanophotonics, okay. It's nano, comes from nanoscale, so 10 to the minus 9 meters. And photonics, photons, light, no? The control of light at the nanoscale in many different ways, no? And so this has emerged as a very, very broad area. It's very, very interdisciplinary because it can borrow elements from, I don't know, chemistry or atomic physics or I don't know, catalysis, etc. So of course, condensed matter theory, quantum, all the way, right? So it's just the control of light at the small length scales in a way such that we can profit from light to do things. For example, we can do sensing of small amounts of an analyte, or we can do microscopy at the smallest possible length scale, or we can understand, I don't know, uncover things that are buried under an interface, etc., etc. No?
Precisely, I wanted to ask you about the specific technique you've discussed in your talk, ultrafast electron microscopy. What's the deal with it? Where is nanophotonics in it? Can you more or less give a picture of it?
Well, in electron microscopy, since the invention of this by Druska, no, in the first part of the last century, so the idea was to use the short de Broglie wavelength of electrons to be able to map small things, no, to basically do microscopy. Then eventually, with the development of electron spectrometers and better resolution for the energy of the electrons, basically to making them monochromatic and being able to resolve the spectrum of the transmitted electrons after interacting with a specimen, then people were able to study the excitations in a specimen, different specimens, no? And so these excitations can be optical, and therefore there can be nanophotonic systems. So since the boom of nanophotonics in the last, I don't know, 20 years or something, no? So electron microscopy has been more and more instrumental in providing information, detailed information of maps of excitations or spectral information combined with nanometer spatial resolution, right? Now, what was missing was the temporal resolution. And then with the field of ultra-fast electron microscopy and basically is to a large extent we thank it to Ahmed Zewail. So basically combines the ultra-fast optics, so the ability to make femtosecond laser pulses with electron microscopy. Now you make the femtosecond electron pulses to generate photoelectrons that are now femtosecond electron pulses, and then you also study with, say, for example, pump probe, pumping the specimen with femtosecond lasers, and then probing with femtosecond electron pulses. Then you gain two things. One of the things is you can synchronize these pulses or study what happens as a function of delay. And so you gain temporal resolution in that range, no? In the range of femtoseconds. And then at the same time you can increase the intensity of the lasers without damaging the material, because it's very concentrated in time, and make the interaction between electrons and light so strong that you basically open up new phenomena that were not investigated before. This strong interaction between light and electrons mediated by polaritons and basically nanophotonic things. No?
And what's the role of a theorist in all of this?
Well, theory has been, I think, driving the field in a way. Of course, this is an experimental field, so you need to produce short electron beams, short pulses, etc. No? But you also need the theory to understand that, and you cannot just do random experiments to see what happens. So with theory, we are able to investigate many of the things that are possible. There are questions that can be addressed with theory much more easily than doing experimentally first. And so this is a bit driving the field. No? And so there have been, for example, predictions of making single photon sources out of electrons, or gaining micro electron volt resolution combined with nanometer resolution in space. These things were easier to do in theory, so I think it's playing a role in understanding and also in helping develop the field.
Yeah, definitely. You've discussed this in the talk, but what are some potential applications? You've mentioned sensing, things like that. How would that work with microscopy?
I think I would like to think of electron beams as another tool to explore quantum phenomena, to also do, for example, quantum sensing or quantum metrology. It's another tool that eventually I hope is on par with photons, no? With photonics, quantum optics. So you can have also quantum phenomena with electron beams, no? Quantum free electronics, right? So that's how I would envision this.
How do you see science in Spain as one of the leaders of a top institution in Spain in research?
Spain has progressed a lot. So when I started my PhD, there were notable exceptions, but not many people who were at an international level in Spain. Now there are many. At the same time, we have some negative effects from history, the historic endogamy in the Spanish university. Unfortunately, this is not yet totally over, but I think that there are many more and more places that are trying to combat that, no? And basically choose their best possible scientists, no? Because that's in their interest. And maybe what I see that is less optimistic from now is regarding funding. So I think we are very limited compared to other countries in Europe, for example, in the percentage of the GDP. But I mean, you can see that, no? That it's hard to survive. So, but yeah, I like to be optimistic, and hopefully society at large, no? And the politicians, as a reflection of that, will just realize that we need science to make society better and to improve our quality of life, etc.
What advice would you give to any undergraduate student, physicist, or in general STEM field?
For me, the most important thing is to live science with and practice science with passion. Right? You have to really feel passionate about it. Otherwise, it's too hard to work on it. No, but can be very rewarding. So I would advise to always conserve this passion. Do what you do, not because you have to get a position or because of the credit or something. Do what you do because you like it. Otherwise, it's not worth it. It's too hard.
Well, that was it for the interview. Thank you very much. I'm sure the undergraduate students will find it very useful, as did I.
Thank you very much for the invitation. It's been a pleasure.